a metal bar with, okay, these are mostly old final exam problems, so I'm not going to worry about the numbers. Again, I'm going to chop these. Since I'm recording, as long as I've done everything correctly, I'm recording this. So I'll put the recordings up on the web. Metal bar has a certain length, certain resistance. It sits on horizontally, so this whole thing is horizontal. On two infinitely long parallel conducting rails that connect to a switch, connect to a battery, connect to a resistor, and then there's another resistor. So the bar has a resistance. There's a resistor here in parallel with the bar once you close the switch, and then there's that resistor there. The metal bar is sitting in a uniform magnetic field that points into the paper or into the screen. And we close this switch. There's a lot of things you could ask about it. All I want you to think about what happens when you close the switch. Close this switch. So before you close the switch, there's a current because of this battery. There's a current through those resistors. When you close this switch, then there's still a current through those resistors. Now there's a current through the metal bar also. The metal bar is actually in parallel with R1 here. The metal bar is in parallel with R1, so there's going to be a current down the page. If there's a current down the page, the direction of the force on that metal bar is to the right. So suddenly, you close that switch, suddenly there's a force to the right on that metal bar. What happens? The metal bar, because there's a force to the right and it's frictionless, the metal bar accelerates. So the metal bar starts moving in the magnetic field, starts moving faster and faster and faster. And what's going to happen when you have a metal bar moving through a magnetic field? Well, there's going to be an induced EMF. As you go faster, the induced EMF gets bigger and bigger. There's no induced EMF when it's not moving. Then you close the switch, it accelerates, so it goes from 0 to faster and faster and faster. As it moves faster, the induced EMF in this bar gets bigger and bigger and bigger. What's the direction of the induced EMF? Well, if this bar is moving to the right, and the field is inward, bar moving to the right, field inward, then positive charge would be pushed upward. In other words, opposite to the direction of the current. There's an induced EMF that's opposite to the EMF of the battery. The battery is pushing positive charge down the bar, and because the bar is moving, there'll be a force up the bar, an induced EMF up the bar, upward. And as the bar moves faster and faster, the induced EMF will get bigger and bigger. Eventually, the induced EMF will be equal and opposite to the battery EMF. And so what's going to be the current then through the bar? 0. But by then, that bar is moving really fast. And so that's as fast as it goes. at the terminal velocity of the bar, the velocity of the terminal velocity of the bar. The question is, find the terminal speed of the bar when the current through the bar becomes 0. Is giving you a hint as to what's going on. Find the terminal speed of the bar is when the EMF of the battery equals the induced EMF because the bar is moving. Induced or motional, sometimes called. Yeah.
When it reaches that speed, we'll just stay with that speed and no current through it.
Pardon me? What was it?
Once it reaches that speed where the two voltages equal, the terminal speed, at that point, will the current stop?
Yes. Yeah, what's going to happen is that there will be a current through the bar. Because there's a current, there's going to be a force pushing the bar to the right. As the bar starts moving to the right, there will be an induced EMF that makes the current smaller. So the current, as the bar goes faster and faster, as long as there's a current down the bar will keep going faster. But that current is going to get smaller and smaller as the bar goes faster because the magnetic force, one way to say it, is the magnetic force upward is going to start pushing current upward is going to start getting bigger and bigger. When the electric force due to the battery downward equals the magnetic force or motional EMF, whatever you want to call it, due to the motion of the bar and the magnetic field upward, when those cancel, then you're at the highest speed you can get.
What will be the minimum current R1? Like initial.
You mean this current?
Yeah, once it's closed, that initial current for R1.
It turns out that this current and these resistors are irrelevant. I mean, they're relevant for what the initial current is and what the initial acceleration is. But they're relevant for that, but they're not relevant for the final speed.
But that current doesn't change through R1, or it does once you hit the junction, because the junction's formed.
That current doesn't change for the current for R. Well, okay, so I'll have to be a little bit careful here. These two resistors are in parallel. Maybe a better way to say it has become just a little bit tricky because the current that goes through the battery also goes through R2 and it gets split between those two in some way. But that split changes with time. Because less and less, as this thing accelerates to the right, less and less current will go through there. And so less and less current will go through the whole circuit. And that means the voltage drop across this resistor is going to get smaller and smaller as time goes on. And, well, I mean, you know about two resistors in parallel. The total resistance of the two yeah, I'm not sure I want to add them together that way.
So will the whole circuit stop or just that loop?
No, there's still an EMF around. The battery is still pushing current through the two resistors. Yeah, absolutely. There's nothing stopping current from going through those two resistors. What happens is that the current that would have gone through this section of the circuit gets smaller and smaller and smaller. It's almost as if the resistance of that bar was getting bigger and bigger and bigger with time. In terms of the circuit, That's what's going on. It's like the resistance of the bar got bigger and bigger. It didn't. What happened was motional EMF canceled the current out. Any other questions about that one? Tricky kind of a thing to think about. Yeah.
So I have a question. Once it reaches like the terminal speed, will it start oscillating back and forth? Because like once it hits that terminal speed, it'll keep going, which means the magnetic flux to it would keep increasing. So would the induced current counterclockwise be stronger, which would eventually like make it all go back in the other direction?
If it reaches it when it reaches its terminal speed, then the increase of the magnetic flux through that part of the circuit stops changing with time. Because the speed is constant. So I don't mean it stops changing with time. Its rate stops changing. The rate of increase stays the same, so there's an induced EMF due to that stays the same from then on. And it's an induced EMF that's big enough to stop the current through the bar from then on. Yeah.
I'm still slightly confused as to why all current, I'm confused as to why all the current would just go through the metal bar and not the resistor once S is closed.
Why it would or would not, or
because the bar provides no resistance.
no, the bar has a resistance of 6 ohms.
Oh, it does. Oh,
Yeah.
Okay.
Yeah, the bar has a resistance
Sorry, I
too.
didn't see that part.
Yeah. So you could, once you close the switch, you can solve this circuit right away for what the current through that bar is.
Okay, yeah.
It takes a couple steps, but you can get the current through that bar. Once you know the current through that bar, you can figure out the force on the bar. You have its mass, so you can figure out its acceleration right away. And that will tell you the speed as a function of time. Unfortunately, the acceleration of this bar depends on the current. And as it goes faster and faster, the current goes down. So it's going to be a force that accelerates it that gets smaller and smaller. So it's only going to exponentially approach its terminal velocity, as terminal velocities tend always to be something like something that's exponential in time. Eventually, they approach the terminal velocity. So initially, the acceleration is big, and then the acceleration gets smaller and smaller. Because the force gets smaller, because the current gets smaller, because the bar went faster and faster, and so the induced EMF got bigger and bigger. So it eventually cancels the battery's EMF. Any more questions on this one? Solving the whole thing is complicated. Solving for the terminal velocity is not as complicated. All you need is the induced EMF equal to the EMF in the bar. Not quite as complicated. And that's when the current through the bar is 0. So when the current through the bar is 0, you know what the rest of the current in the circuit looks like, and so whatever the EMF across this bar is gets canceled by the induced EMF of the motion. And at that speed, you get it. That's where it's at terminal velocity. Any other questions about that? Yeah.
So the current through R1 would be cut in half as soon as the switch is closed, and then go back to the original magnitude once it's we determine what's it.
Well, I mean, it's not cut in half because what happens when you before you close the switch, this is R, that's R. Before you close the switch, that's E. Before you close the switch, the current is E over 2R, right? After you the instant you close the switch, suddenly there's another resistance that happens to be the same. The bar is sitting there. And so these two together add together to give you a total resistance that's smaller. Whenever you have resistors in parallel, you end up with a smaller resistance total. And so this is R over 2, that's R. And so the instant you close the switch, you raise the current in the circuit. You don't cut the current here in half. What you cut in half is a larger current because you have to take into account this 6 ohm resistor also. In fact, if this 6 ohm resistor wasn't here, when you close the switch, you wouldn't raise the current at all. If this 6 ohm resistor wasn't here, the voltage or the EMF across R, this one, would stay the same whether that was closed or not. So as written, you do have to deal with the whole circuit to figure out what the current is through the bar. This is just I total. The current through the bar, this is I total at T equals switch closed. The current through the bar, it turns out, is half of that. At T equals switch closed. Just because the bar and that resistor have the same resistance. So the total current does get split, but the total current got bigger as soon as you close the bar. Any other questions about that? This is like a combination of, this is about as complicated a combination of electrical, DC circuits, induced EMF, and forces, magnetic forces. This wraps them all into one.